Hi folks, let's get back to it. We're currently discussing compact linear transformations between Banach spaces, and at this point we know some of their basic properties. We're gradually going to build up more theory, eventually leading to these so-called spectral theorems for compact linear transformations on certain Hilbert spaces. But before we get there, we need further properties, one of which is still displayed here on the slide. So I started proving this last time, and we're now going to finish its proof. The statement is as follows: if you have a compact linear transformation between two Banach spaces, then that guy is going to map weakly convergent sequences in X to norm convergent sequences in Y, right? So the proof is almost complete. Let's go through the steps quickly, the steps that we already carried out. So if you have a compact linear transformation and a weakly convergent sequence, then the image of that sequence is also going to be weakly convergent. That is a general effect of bounded linear transformations. This doesn't use at all the compactness of the operator, right? It uses instead the dual transformation. All right, so then we have a weakly convergent image sequence y sub n, and the limit we call, well, it's written here, t of x, and that just for abbreviation you call y. All right, now you assume, well, it's going to be proved by contradiction from now on, that that sequence does not converge to the same element in norm. All right, that is to say, there must be then some subsequence that stays sufficiently far away from y. In that subsequence we denote y sub nk, and sufficiently far away from y is here quantified with this little quantity epsilon. All right, so but now what you realize is that the y sub nk, it corresponds, of course, well, y sub n is already an image sequence, so the yn sub k, the subsequence, is also going to be an image sequence, and it corresponds to t sub x nk. Yeah, but since our initial sequence at xn was a weakly convergent sequence, that implies that it's in particular bounded. This is one of the properties of weakly convergent sequences. They are bounded, right? So in particular, that subsequence is bounded. So what you do here is you create an image sequence y sub nk starting from a bounded sequence. Now the compactness kicks in of capital T, which says then, well, there must exist a further subsequence y sub n sub k sub m, such that that thing converges in norm, right? Because remember, compact linear transformations, they map bounded sets in X to sequentially compact ones in Y, and that's precisely what I'm exploiting here, right? So now our subsequence y sub n sub k sub m has a limit as m goes to infinity, denoted y hat. But now I claim, and I said this in words last time, but this is impossible. Why? But this is impossible since then, so what I just concluded from the compactness is that the y sub n sub k sub n converges in norm to y hat. Yeah, but norm convergence implies weak convergence. This is also one of the properties that we discussed a while back. Since then, we would have y sub n sub k sub m also goes weakly to that y hat as m tends to infinity. And so we must have that y hat is equal to y, since, well, weak limits are unique. That is also a property. And why should the y hat be equal to the y, since weak limits are unique? Well, let's just go back here. So up front we had this little statement here that yn converges weakly to the element y. Yeah, but that means in particular all the subsequences thereof will also converge weakly to the same element, right? So in particular this subsequence y sub n sub k sub m, as m goes to infinity, is gonna converge to that element y. So in other words, this y hat here has to be equal to y. And that's precisely what I'm writing up here. Yeah, but now once this is established, you just go back and you find out that y hat is equal to y, so that means y sub n sub k sub m actually converges in norm to y. Yeah, but this is contradicting our assumption here. Suppose that yn does not converge to y in norm. Okay, so that's the contradiction. Okay, since are unique. All right, for this reason, we must have the norm convergence as n tends to infinity, and this completes the proof of our theorem. All right, so that's an important property. The compact linear transformations are those guys that map weakly convergent sequences into norm-convergent sequences. Well, that statement is not quite true. One of the properties of a compact linear transformation is that it maps weakly convergent sequences to norm-convergent sequences. Now, the question whether you can classify all a compact linear transformation by that property, that is a harder question, and in general it is not true. I will write this here in words. The converse of the last theorem holds only if capital X is a reflexive Banach space. Right? If you are in a non-reflexive Banach space, and we discussed examples, then this is in general not true. Okay, but this is a deeper result. In the lecture notes, I give a reference to the Simon Reed text, and you can have a look at this theorem. It's not super hard to prove, but it requires further theory that we haven't developed in this module and that we won't develop. So that's why I just leave it at this comment. In fact, if you ever take a class on operator theory, then likely this will be discussed, because the bounded linear transformations that map weakly convergent sequences to norm convergent sequences, they are usually called the completely continuous linear transformations, right? And so what we just figured out is that if you have a compact linear transformation, then it is completely continuous, but the other direction only holds true if you're in a reflexive Banach space, right? But I will leave it at this. Okay. Instead, we will now move ahead, and now the immediate goal will be to show that actually not every bounded linear transformation is a compact linear transformation, and at this point we actually don't know that yet. Okay, so and here's the little helper that will yield that result. This little helper on the surface has nothing to do with compact operators, with operators in general. It's a statement about normed linear spaces. So let's go. So if X is a normed linear space and you have a closed proper subspace, proper means that the complement of Y in X is non-empty, right? So you can certainly find an element which is in X but not in Y. That's what proper means. Okay, closed subspace, that should be clear what that is. And the statement is as follows: for any given epsilon, you can find a vector in the normed linear space with unit length, and it keeps a sufficient distance from your closed subspace, right? So the distance of X to your closed subspace is at least 1 minus epsilon, right? So you can almost, in other words, you can almost make the distance equal to 1. Not quite, right? Because epsilon is strictly positive, right? So okay, good. So let's prove this guy. And then once we have proven it, then I will show you how you can use this to prove something non-trivial about compact linear transformations. All right, so first, let's take an element in that complement. And as I said, since we have a proper subspace, that element exists. Then what we note is that the distance of this element, well, as you probably would imagine intuitively, but usually that intuition is based on some finite dimensional pictures, and they might fail, but nevertheless this is true. So you have an element in the complement, and if your subspace is closed, then indeed the distance between that element and the subspace is positive. All right, so why is this? Well, contrary, if the distance were 0, the distance is an infimum as written up there, then of course you can find a sequence in Y that creeps up to your element. Then there exists, or more mathematically precisely, that converges, not creeps up to Z. Then there exists Yn in Y such that Yn goes to Z as n tends to infinity, but Y is closed. So, well, closedness you characterize precisely by convergent sequences having their limit in the set, right? So we must have that the limit z is in y. And that's a contradiction to your initial choice, right? Because it's not in y, it's in the complement of y. All right, that's why that distance has to be positive. Okay, moving along, moving ahead. How do we find this element? So first, without loss of generality, we may assume that the epsilon does not exceed 1. Well, because if epsilon exceeds 1, then this would be here a negative number, and then this inequality is trivially satisfied because the distance here is always a non-negative number. It's an infimum ranging over all possible distances between your point x and the closed subspace y. That's always going to be non-negative, right? So there's no shame in here assuming that epsilon is strictly less than 1. Okay, without loss of generality, let epsilon be between 0, 1. And then I claim we can find an element, call it y star, which depends on epsilon. I will indicate it in this way, so that first of all, z, the distance of z minus y star, this is going to be positive. That we already figured out earlier because z is in the complement, so that distance is going to be positive. But now the more important part is that the distance of z to the initial point z to y is bigger than, well, 1 minus epsilon times the distance of z to y star. So in other words, this one. So why is this true? Why is this true? So if not, what's the contrapositive of that statement? Then for all y in y, you have z minus y, well, the reversed inequality, right? Distance zy 1 minus epsilon, right? If this statement were not true, then for all points y in the subspace, you would have the reversed inequality. Yeah, but if this is true for all y, then it's in particularly true for the one that minimizes the distance to z, and that's, well, the infimum, right? So from this on, you were to conclude that the distance between z and y, just optimize it over all y and y, has to exceed the distance of zy 1 minus epsilon. Yeah, but now this distance is positive. That's what we showed in the first part, so you can naively divide it out. And then what you have here is the fantastic contradiction that 1 minus epsilon is at least equal to 1. And that's a contradiction because then epsilon would have to be 0 or negative, and that is not going to work out with our assumption here. Okay, so that's why everything that is written in yellow is false, and that's why indeed you can have this element, you can find this element y star in the indicated fashion. Okay, good. So now moving ahead, setting, now here comes the actual x that we want, x epsilon, which is z minus y star. It's used to be normalized. So I'm not dividing here by 0, right? So that is clear. The distance is positive because the z is in the complement of y. We have, well, okay, x norm is equal to 1. That's clear. And for all y in y, let's do some algebra here. So x minus y. Okay, so I have z minus y star, z minus y star minus y. And now you do the algebra, you bring it on the common denominator, and then the denominator is a norm, so it's a scalar, so it comes out of the total norm, and then you have something here on top. And that, if you, well, allow me to skip one step, which is factoring out a minus sign, then you will have z minus y star times y. Okay? But now notice, we haven't used so far that you're actually playing around with a subspace. Right? So, but now we do, because y is an element in capital Y, and also my element y star was, by choice, in y. So then that means in particular any linear combination, such as this one, is going to be an element in y. Yeah, but the lower bound then for this is, of course, the distance of z, which is sitting here out front, to capital Y, right? So that is the green input here, okay? And that is the yellow input. Okay, and the denominator is just the same, z minus y star. And now if you remember how we chose on the previous slide that z minus y star and the distance with the 1 minus epsilon in the denominator, if you just use this inequality, then this is indeed bigger than 1 minus epsilon. All right? And this equation here, what I just did, this here, the inequality, not an equation, the inequality holds true for all y in y, and then you take again the infimum over all y's in capital Y. So the distance of x to y is at least 1 minus epsilon, proving our claim. Okay? That's the end of it. This is called, by the way, I think I didn't say that, Riesz geometric lemma. Riesz lemma. Okay? As a result in the theory of normed linear spaces. But now, why is it useful here? Well, because of the following consequence. Proposition. And if someone ever asks you, can you name a linear operator which is not a compact linear operator, do remember this result now. So because it's the trivial, the easiest non-compact linear operator. Let X be an infinite dimensional Banach space. This is clear. I already said at the very beginning, if you're working over finite dimension, everything is compact, so that there's nothing to learn from that. But if you are then in an infinite dimensional Banach space and you know plenty of those guys, then the identity on that space I sub x is not a compact operator. All right? So that's the simplest non-compact operator if you're over an infinite dimensional Banach space. Right? So how to prove it? So now for this one, we have to construct, well, so how do I prove that something is non-compact? Well, I have to find a bounded, bounded sequence, say, which doesn't have any convergent subsequences, right? Because then it means it cannot be compact. Because by definition, compactness means you mapping bounded things to sequentially compact things, right? So, and how do I construct such a bounded sequence that does not have any convergent subsequences? Well, that's precisely what the Riesz lemma will give me. That's why I discussed it up front. All right. So suppose here's the construction. X is infinite dimensional. Then pick an arbitrary starting point, x1 in X, not the 0 vector, but a vector with length 1. Now set x1 as, well, the span, so just all scalar multiples of your x1. Now this guy is gonna be what? It's a closed, well, it's a finite dimensional subspace, so all the finite dimensional things are closed. I mentioned it when we discussed the equivalent norm theorem. It is a proper subspace because you are in an infinite dimensional vector space. So everything that is finite dimensional in there is proper. Okay. In particular, this one-dimensional thing there, capital X sub 1, is proper, which is closed, which is a closed, proper, well, okay, let's write it out. One-dimensional subspace of X. Thus, by the Riesz lemma, you can find a vector x2 of unit length, x2, which is actually in the complement of x1, with unit length, and you can put sufficient distance between x2 and that proper subspace. And here's sufficient distance. Remember, it was 1 minus epsilon for any positive epsilon, so let's choose epsilon 1/2. So I can put distance at least a half between that, but that implies in particular that the distance between x1 and x2 is at least 1/2. Okay, and maybe now you can already foresee what I'm going to do next. Now, given that new vector x2, what I'm going to do is I'm going to create new subspace, capital X sub 2, which is the span of x1 and x2, right? And this is again a closed, proper, two-dimensional subspace of x. By the way, the x2 is not a multiple of x1, so because it's in the complement, right? Good. And then once you have this subspace, you again apply Rie's lemma. You find vector x3, which puts distance 1/2 between x3 and that capital X sub 2, right? And then you continue. So given this, we inductively construct an infinite sequence x sub n, and all of these x's, they will have length 1, norm 1, right? So that means in particular they're going to be a bounded sequence. In particular they are in the closed unit ball, all right? So that between all their terms you have at least distance 1/2 for all n different from n, right? But clearly this sequence has no convergent subsequence. Subsequence, hence this ball here, B1 closed, which is the image of the identity under B1 0 closed, is not sequentially compact, and hence the identity by definition is not compact. It's not a compact operator. Okay, that's it. All right, so that's how you prove that non-compact things indeed exist. You just go to infinite dimensions and you look at the identity. All right, so now this has a few corollaries, two actually, that I will quickly write down. So if you have two Banach spaces and at least one of them is infinite dimensional, then any compact linear transformation between those two spaces is not invertible. Okay, invertible. All right, so in that regard, the compact ones don't seem so great because you can't invert them if they act between infinite dimensional spaces, but that's just a minor issue. I should rather call it a feature of them. How to prove it? Well, if T is compact and if it were invertible, and then by definition of invertibility there exists an inverse T minus 1, which is a bounded linear transformation from y to x, so that T minus 1t is the identity on y, and the other way around you create the identity on x, right? But now remember the ideal property for compact linear transformations. By assumption, this is compact, and likewise this, which is the same thing. And now what you do here is you compose it with something bounded linear. And remember property 3 and 4 of the very first theorem on compact linear transformations. It says if you have something compact and you compose it with something bounded linear, the result is still going to be compact, right? So this would mean that at least one of these guys, right? At least one of these guys here. No, that's wrong. It would mean that both of these guys are compact, but that would lead to at least one contradiction, because up here it says at least one of these Banach spaces is infinite dimensional, right? So you get at least one contradiction out of these two yellow bubbles, because we just showed up there that the identity on an infinite dimensional space is not compact. All right, let's write this down in words. We thus get Ix compact X and IY compact Y. But at least one of those statements is false. At least one of those implications is false by the previous result. All right? And that's why our assumption was false, and hence compact things are not invertible. All right? One more corollary which rephrases this in terms of the spectrum. So if X be an infinite dimensional Banach space and T compact, then 0, the scalar 0, is always in the spectrum of T, right? So, and why is this? Well, because if you have an infinite dimensional Banach space, the previous corollary just showed then your operator is not invertible, right? And not invertible, that means, remember the definition of resolvent operator and spectrum, that just means that lambda equals 0 is in the spectrum, right? Because then lambda I minus t, which is at lambda equals 0 precisely minus t, is not invertible, right? So that means lambda equals to 0 is in the spectrum. That's precisely what's written there. All right, I will stop now. In the next video, we will discuss ultimately we will discuss a test that allows you to check whether certain things are compact or not. But before we formulate that test, we need a second special family of bounded linear transformations, the so-called finite approximable linear transformations. All right, we will define what that is, then we will study basic properties, and then we will formulate and prove the compactness test. Okay, I will see you soon.